I am someone who enjoys to play with microcontrollers, and I have made some interesting experiences in trying to teach people about it. So I am here today. I would like to present you with one way which is not so well known but should. So initially, let me ask you, who of you has played with microcontrollers, any sort of microcontrollers? Who of you is still doing that? Okay, not so many dropouts. Who of you have used Atmel 80 mega microcontrollers before? Well, it's almost everyone. Cool. The title of my talk mentions the word Arduino, and what I present does work on an Arduino, and I have one with me in case you wonder. But I prefer this type of board for the simple reason that I can add stuff here. And here I need to have a shield and add stuff to the shield, which I don't like too much, but that's just a matter of personal preference. So, playing with microcontrollers is actually not as easy as you might think if you don't know about it. You need quite a bit of stuff up and running, and there is no way around it. You need a controller, obviously, and a board and power and things like a dongle to put a program onto the controller like this one. You need a fairly long list of software, like your favorite editor. You need an assembler which will convert what you wrote into a format that the microcontroller will understand. Then you need a flash tool which will transfer what has been assembled down to the controller. For the stuff I am presenting here, I also need a serial connection, and on the other end of that serial connection, a terminal program such as Minicom or Hyperterminal or whatever you have. I am presenting this list for a reason, because every single one of these steps may fail at you, and they are hard to debug and hard to find out sometimes why things don't work. So, in order to make this more simple, I wrote an article which is available at the same, or will be available at the same place where the slides are, and I typed down what I think you need to know in order to get through this. Today, I will skip all of this because it just takes too long, and have a look on your normal work cycle. You normally, or if you, the way I have started, that was some 10 years back with microcontrollers. I used big microcontrollers by Arizona Microchip, and workflow would go like, well, you edit some file, obviously, you have to assemble it, you erase the controller, you reflash it, and then you reset and watch the result of what you have done. Now, you repeat that until done, or until you run out of time, whichever happens first. A thing that has been forgotten by many now, fortunately, is when I started, I had to remove the controller from its board, put it into the programmer, reflash the thing, and then put it back. And the erase part of that used to be difficult long times ago, when we had to erase microcontrollers with ultraviolet light. So why some time, and for every cycle, even if you change only one bit of your program, you have to go through this. Now, maybe there is another way of doing this. Something like you log into the controller, well, the controller is not a Linux system, so logging in obviously is hard to imagine. You compile new functions, new tricks to the controller, and test and use them right away. Now your repeat until done covers only 2 of those points. And this is the part I would like to demonstrate today. Obviously, there are 2 steps up front. The system I'm going to present is called amForth. You need to assemble and flash a controller with that system. The system needs to be configured with things like what is your crystal frequency, what is your precise model of controller, how fast is your serial line going to be. And once you have that, you put this system onto the controller, and then you can play this game that we would like to get at. Log into the controller, work with it interactively, and use the new stuff you defined right away without going through the assemble and reflash cycle. Now, what is amForth? amForth is a small system. It's an incarnation of a well-known programming language called Forth. It was developed by a guy called Charles Moore in the beginning of the 1970s, so you may call it old or mature, whatever you prefer. It's interactive. I elaborated on that a little already. Still, it is not interpreted. It's running all compiled code. What you really do while programming is you extend the available words in your language until it fits to your problem at hand. And then you run that. It is stack-based, which means no argument lists. There is not much syntax in Forth. The only thing that you need to adhere to is you separate tokens from each other by white space. That's about it. And everything is postfix. So this needs a little getting used to, but after a few rounds, you will be able to go through that. I prepared 3 examples here, which I'm going to demonstrate now. One is a Hello World program, which does not involve blinky LEDs. The other does. And the third is a more elaborate example I chose to show here because blinking LEDs is not showing some of the nice features of working with amForth. The demo system, which I have here, is featuring an 80 mega 32 controller. So it has 32 kilobyte of flash space to cater for the amForth system and any code you write. It's running at 11 point some odd frequency. This is a baud rate crystal, so my serial line is happy about that. I have made a comfortable amForth system and already loaded quite a bit of words onto it in order to make this presentation work. Everything of that has been wrapped into a tar archive ball, which should be available at the download site as well. So the code I'm presenting now is available and you can use that. Okay, so let's see whether we can put the reset switch on this board. So if everything I have mentioned so far is working, you will be greeted by this line. So I have logged into the controller, sort of. There's no password involved or things like that. But I'm there, and if I put the enter button, it will say OK, which basically says it has done everything I asked it to do, namely nothing. Now, what is the language that this controller is understanding? We could try help here, but it won't lead us anywhere. The magic word here is words, which does list a fair amount of stuff. Words in forth can be called anything. So further down this list, you'll find words like these, right? They are hard to read, and no one knows what they're doing. But they also show what I have said. You can call your tokens anything you want, and they are separated by white space. So, I'm going to clean this up a little bit by typing in start. And this should remove all the words that come after the start. Did I mention it is case sensitive? So if I ask words again, there should be a few less now. Yeah, it has erased everything from this word start, which is called a marker. This is your way to clean up the controller after you spend a few hours hacking and want to get rid of all the unsuccessful tries. So that's what I did here. Can I define a new word? Can I teach this controller on the spot something new? I can. So let's define a new function. The colon is one of these odd words. The colon says, please start the compiler. And the colon will consume the next word which I type in on the input stream and create a new entry in the word list with the name hi. And then I teach it to greet Fosden. And then I want it to add a new line to the output. And then I say, I'm done. The semicolon is the end of my definition. So it will say OK, which is good, because if I'm going to present an error message, I call a word which doesn't exist, so you get something like this. This is in sharp contrast to what David Lechner was talking about just an hour ago. Well, it says, you made something wrong, go back. Now, next thing, can I use this newly, are you going to believe me that it's in the word list? Yes, it is. It's called I, right? So let's call it I. And it does exactly what I told it to do. And again, let me stress, I have not reassembled, reflashed, re-downloaded anything here. Okay. So that is the first demo, but that's not really an embedded demo. An embedded demo always involves blinky LEDs, because that's all you've got on your board. Now, I have thought about LEDs look like this. They are too small to be seen far away. So I gathered the remains of an old Nord light, which has a few more LEDs, and connected them to port B on pins 0, 1, and 2. So the next thing is to demonstrate how can I make this work. I mean, you are not going to believe me, I can't do here anything before those blinky lights blink, right? So you can go and define the register address for hex 38. So hex 38, which you have to look up in the data sheet, and give it a meaningful name. Constant port B. Now, if I call this new word port B, the fourth guy is called everything a word. You can call it a function, a procedure, whatever you like. The fourth guy is called it a word. Now, what does this thing do? I defined it to be a constant to produce the word hex 38, but I don't see it here anywhere. Do you? I don't. It has put it onto the stack. The stack is a simple first in, first out piece of storage in RAM.
First in, last out. First in, last out.
First in, first out. Now, first in, last out. You're right. He's right. I have a few words I have quite a few words to deal with the stack. So, the next thing I want to show is the word .s, another one of these incredibly short words, which will show the content of the stack. It's 56. Something went wrong, maybe. But this offers the opportunity to introduce another concept of fourth. Everything numerical goes through a thing goes through a stage where a given base is being used. So I put in the number in hex format, and I am suspecting it's putting it out as decimal. Now, if I switch back to hex mode and ask it to produce the stack again, it will be obviously 36 in hex. So if you want to know what 220 in decimal is, so I say I put in a number in decimal notation, the ampersand will tell the compiler or the parser of the loop, well, what comes after that ampersand is really in decimal notation, no matter what the current base is. And then I pop this from the stack and put it out, it's DC. So if you wanted to have a cheap hexadecimal converter or binary for that matter, here is one. Binary works the same way. It's 2e. Well, you have known that. Okay, so I created a constant, and I'm going to need another constant. It's 37 hex. It's 37 hex, and I call this thing DDRB, Data Direction Register for port B, right? And this is the way it goes. This is what you get from your data sheet. Now, I need to set the bits in the data direction register to 1, which I will do now. There's another one of these odd words. Now, still nothing is blinking or has changed here, but that's to be expected because I have to set, in this case, once to the port itself. And nothing happens. That's not what it should be. I can test this with this stuff. There's something went wrong here. Yeah, there's obviously no connection, so that's easy to fix. Believe me, I have set several nights on a problem which didn't work, and eventually it turned out that there was no connection. So let's see whether this nothing changes. That's really not nice. Now we go.
Yay.
This at least should demonstrate well. If I have a board that has some fancy periphery connected to it, and it doesn't work, so I can go in with Forth and change individual levels on individual pins. I can create pulses, all the stuff needed to talk to this external periphery. And I still don't have to reflash. So, I would like to go a little bit about postfix notation. Postfix notation is simpler to parse, so if I put in numbers and add them and show the result, that's always unambiguous. Every word will fetch its arguments from the stack, deal with them, and put any results back. So if something doesn't work in the beginning, it's probably that you did not document or understand the stack effect involved in your new word. Now, postfix notation for arithmetic might be familiar to many of you. However, in Forth, this doesn't stop at arithmetic. It's used in control loops as well. So I would like to show one example. I define a new word, it's called odd, and it will take one argument of the stack and put back a true or false flag. What I typed down is a comment. The comment needs to be, the parents need to be enclosed with spaces, otherwise it doesn't work. So, if the number on the stack is odd, its lowest bit is set. So I'm going to mask out the lowest bit, and if that expression goes to true, I return a true here. I don't need to really do that here. This is just a demonstration. How would I write down an if-else block? It's all backward. So, as a rule of thumb, in Forth, everything is backward. Now, the next example is a bit longer, and looking at my clock, I might need to take a few shortcuts here and there. I am I have connected two items here which are connected to the controller on its I2C square bus. The inter-IC bus is a thing which was developed by Philips some time ago. If you look for that in the data sheet for the Atmel controllers, it's called TWI, two-wire interface, probably for the reason that they want to avoid paying license fees to Philips.
And that won't avoid paying, period.
That won't? Okay, so in the data sheet it's called two-wire interface. Now, what I want to demonstrate is that you can bit bang such a connection and everything we need to do that we have already. So, we have three LEDs here. Let's put in a marker here again to clean this up. Port B, pin 0, I define a new thing. It's called port pin and it gets a new name, blue. The interesting stuff about what I do here is that port pin colon is a word which will define itself a new word. This is where the extensibility of Forth comes in. I can even create words which will create new entries in the word list themselves. Red. Nah. Well, it told me I did it wrong, so. I want to use port B, pin 3 and 4 for the two-wire connection. So we add two more words here. Port B, port pin, colon. Yes, let's use this as the data line. There's a number missing. And port pin 4 for the clock. I have done this before, this is a shortcut. I need to initialize the pins. I can do this individually, like so. I can say the data line should act as an output pin. You don't see any response here, but it will set the corresponding bit to this pin in the data direction register. So the controller acts on this pin as being an output pin now. We need to do this for the clock pin as well. And as I said, I think I have done this before. Now if I change something here, like blue low, blue high, yeah. And the high is in inverted logic, so the high will switch it off actually. Now, a common problem in dealing with microcontrollers is that you need to wait some time. And waiting is always done by wasting CPU cycles, unless you have some advanced scheduling system, which we don't have here. And I would like to demonstrate one other concept, which is something like a function pointer in other languages, which means I'm going to define two different wait functions. one that waits long, one that waits short, and I decide later which of one I want to use in a given piece of code. Yeah. So let's call this wait long, and a wait would be for 500. Counting from 0 to 500, do 1 millisecond delays and repeat that. And so if I call wait long, it should take another half second before my prompt comes back. Now we do the same thing, and it's called wait short. And we do this just with 50 milliseconds. Again, everything is backwards. From 0 to 500 backwards, do something, loop, go to the beginning of the loop again. I define a thing called a deferred word now. Deferred. Deferred means it's a pointer. It's not actually the function itself. It's pointing to a function eventually. Now, if I want wait long to point to wait, I need to tell the compiler, I need to tell the system. So I define a word called slow, and this magic produces the entry address of wait long, puts it on the stack, and then magically copies it into the place which wait, the deferred word, is providing. So I need to call that, and I'm going to demonstrate this in a little bit. We need the corresponding word fast, which will produce the entry address of no op, and put that into wait. So I want to show pulses on one of these LEDs. So I define a word called pulses, which takes a number from the stack and puts back nothing, and the do will consume this number. So we say red low, wait, red high, wait, and we are done with the loop, and then we are done with the whole definition. So if I'm lucky and I say 10 pulses, no, it did it wrong. Something working here is. So obviously we can do this. Now, this is the slow thing, right? We have to wait until it's done. It's done now. So I switch this to fast mode and call it again with, let's say, 100 pulses. See it? It was fast. I think this is one of the more amazing concepts in Forth, that you can at runtime rearrange things by just using function pointers. So in order to do this, I'm going to change from my original schedule now and call this up in the editor.
When you say you don't reflash the port, does that mean that all the new words are stored in SRAM?
No. That's a good question. The question was, let me rephrase the question into, now if I unplug the controller and it has no electricity and I plug it back in, has it forgotten everything? No. The amazing thing with amForth or any Forth is that it compiles what I defined into Flash. If Flash is where my programming my program is stored, so it's not lost. I need to take care about initialization sequences, obviously, but nothing is lost. So let's find this. So I should maybe make this a little bit bigger. Where is the bigger thing with the yeah. Can you read this? No, not really, right? Anyway, the way this thing works is you start bottom up. You start with a very small part of your problem. I came up to the pulses thing, right? So pulses, make a loop, switch on and off one of these LEDs. Now, for talking to the two-wire interface, I do the same thing. I do a very small bit of functionality which will read a given bit, assert this bit on the data line. If the bit is set, we put the data line to 1. If not, we put the data line to 0. And then after that, we clock this out by asserting a 1 on the clock line, waiting for a little bit, and going back to 0 on the clock line. And wait entirely for symmetry reasons. So, then you need obviously some way to extract a bit of a given position of the word you want, or the byte you want to transfer. So this function takes 2 arguments from the stack, namely the byte under inspection and the bit position, and it will put back the value of this bit. So let's demonstrate this, because this is where stacks and things come in. So what did I do? I said one swap L shift. I put 2 bytes onto the stack, namely, let's say EA, and I want bit position 3 of that, right? Now, if I look at the stack, I have the 3 and the EA there. Then I add a 1 onto the stack. I exchange the positions of the top 2 entries with swap. And then I do an L shift. Which will leave me with the bit mask. And then I do an AND, I believe. Let's check here. I do an AND. Dot S. And it returns an 8, which basically says, yes, this particular bit was set. Let's see whether we can verify this quickly. The original word was EA. EA, I go to binary mode and print it out. And position 3 starts at 0, is set to 1, so we are all set. The next thing I'm going to do is that I use get byte and clock out 1 bit in the inner part of a do loop, which will iterate over 8 bits, and it will produce the bit in question, putting out most significant bit first. And then I'm all done to transfer 1 byte. Now here I made a copy of the original byte because it gets lost in the process extracting this one particular bit, and it's still there after the loop ends, so I need to drop that explicitly. Then we need a few more things like producing a start and a stop condition and reading the acknowledged back from the bus. Reading the acknowledged back is plain text. You switch the data line to input mode, you wait a little, and then you read the value of the input pin, and then you put it back to output mode. That's all there is involved in here, and you wait a little. You tell the addressed device to produce its acknowledged bit by clocking out one pulse on the clock line. So this is what these two lines are about. Assert the clock and hear it again. That's everything. That's everything you need to do in order to put out a byte and read the acknowledgement. And so I brought with me this little thing, and yeah, it's tiny, but let's see whether we have the words still on the Now, what I'm going to do now is I upload the file I prepared with the code. Once you are done with a cycle that I just demonstrated, you want, of course, to store this in file format, and you want, of course, to have a way to read this file to a new controller. And amForth comes with two tools to do that. One of them is built in to Minicom, not in this one, so tough luck. There is a little program donated by one of the amForth users. It's called amForth Up, and you can plug it in here as a transfer tool, and it will read the file you edited, which contains Forth code, and read it to the controller, thereby waiting for the echo character to be received after sending one byte. Always wait for the echo character, and after sending a new line, it will wait for the OK or the error message to appear. If it's an error message, it will stop at this place. If it's OK, it will continue. So we need to do this a little bit different here. I'm a lazy person, so I created a makefile which will basically call this line. There is a tool, a Python tool coming with amForth, which will read the file to the serial device you give it. The two lines before that are filters, which you will find in the tarball as well. I am an impatient person as well, so I don't want to wait for all the comments to be transferred to the controller and then thrown away. Okay, let's try whether we are on the right track here. The name of the file is main.fs. What's this? Yeah. This is the program reading my entire file to the controller. And in case I'm lucky, it will just go all the way through, and then I can log in again and use everything I have in the file. The last part here is what I'm going to call run. It will do all the initialization that you have seen before, and it will transfer a 0 to this device. This device is a 8-bit I/O controller. It reads what it needs to do from the two-wire interface and then switches things accordingly. So there is a variable involved here. It's called n. We get the value of n inverted just to make it better recognizable, and transfer this byte to this device, and then increase the value of n and wait for a second and repeat this cycle. So what you want to see here is blinking LEDs, right? So we have all this, yes we do. So if I'm lucky, this is going to work now, right? Yeah, cool. If you look on this part, the transportation of the bits is indicated by switching LEDs on and off. And if I make it slow, if I go back to this function pointer, wait, and put in the address of the slow address, this will be much slower. However, let's see whether we can do this really quick. AA, transfer this to the make it slow, right? So now you can see the bits being clocked out. This is very helpful for debugging. This is pretty much everything I have prepared, so let's go back to my slides where all the code is, right? So what is this amForth thing? It's a standalone for 80 microcontrollers. The maintainer's name is Matthias Trute. It's free software. It's under GPL version 2. It's interactive. I hope I have demonstrated this part. Everything is compiled language. It's extensible. It fits into 8 kilobyte of flash, including the compiler. So if you go and buy a controller for playing with this, get yourself one with 16K of flash or larger, because the 8 kilobyte are almost used up by the amForth system. It's stack-oriented and postfix. I have said that it's case-sensitive, it's without safeguards. If you do it wrong, it will hurt you. It comes with a collection of library modules. There is a collaborative multitasker. Collaborative meaning the programmer will decide for every task where is the best place to interrupt the task, and we'll call a word called pause. And then all the tasks are being run in round robin. Math things are in scaled integer. There is double cell arithmetic available, so you have 4 bytes of data space there. There's also a floating point library module, which I haven't used myself, so I can't talk about it. There are up to 8 active word lists. Everything is organized in word lists, and you can have several of those, which may present different types of user interface. There is a loadable assembler. I'm running out of time here. I have 5 out of many sources about amForth. The most important obviously being the amForth webpage at SourceForge, together with a bunch of stuff. If you are interested, go back to my slides and my little article